Mike Mitzenmacher, Gopal Pandurangan, and Scott Roche. Chinmoy is at Twitter, Mike Mitzenmacher at Harvard, Gopal Pandurangan at University of Houston, and Scott Roche just completed a PhD with me at Northeastern. Okay, so I know this is the last talk before everybody leaves, so I'll try to stick to our time. So this talk is somewhere, considers a model that is, looks at applications somewhere similar to what Professor Ganesh talked about and what Professor Kiwi talked about. So it looks at what we call Cobra random walks, in keeping in spirit with the snakes that we encounter here. But it's a fairly simple process. So what I will do in this talk is introduce the process, work through maybe a couple of examples on the board, and talk about a couple of somewhat technical results, but then depending upon how much time we have, we'll go over the proofs there. Okay, so there are many modes by which epidemics and information spread, and a lot of this have been studied. Simple random walks, rumor spreading mechanisms like what Marcos talked about, random walks with speed-up techniques, parallel random walks, the SIR and SIS models that Parangonas talked about, and also Ganesh talked about earlier. What this talk is going to talk about is a very specific kind of a walk. So, and there are a bunch of open problems. At the end of the day, if all you get is the definition of the process, hopefully you'll come back and solve the open problems by tomorrow, because it's a very simple process. So the process is as follows. Some node of a graph starts with a token. Okay, think of it as an infection piece of information. And it spreads information or spreads this infection by sending it to k neighbors. Any node infected at time t, at any particular time t, spreads this infection to k neighbors. However, a node doesn't remain infected forever. So this is like at each step, every node that is infected, which is active, infects its neighbors, but then it itself recovers unless it's infected by any of its neighbors. Okay, so here is an example. Okay, so this is a formal definition. You have so throughout this talk, we'll be focusing on finite graphs. So it's an arbitrary graph G. We pick any vertex u prime, place a token at that. For each u, if there is more than one token at node, all tokens at that node coalesce into one. Each token then becomes k tokens, which is the branching. For each u, each token at u independently chooses uniformly at random some neighbor and moves to it. Throughout this talk, we will assume, even I've talked about these k tokens and this k branching factor. Throughout this talk, we'll just assume k is 2. Okay, so here's an example. So this is an illustration of a Cobra Walk. So initially, one node is infected. At this time, this node picks 2 random neighbors. Imagine there was one token sitting there. It splits into 2 tokens. Those 2 tokens each make an independent random walk and go, in this example, to 2 different nodes. They could have been gone to the same node. That would have been also fine. Each of those 2 infected nodes pick 2 random neighbors or with repetition, and you get these 4. And then you have, so in this example, this node picks 2, one of these 2. This node picks 2, but both of those will be the same one here. So we get, now we have 2 infections here, but they coalesce into 1 infection, and that becomes active. I just, for concreteness, it's just some arbitrary number k. In general, you can analyze more general books. Oh, good. Okay, so why the question is why there is a fixed number. You could generalize this model to adopt a different branching factor at different nodes drawn uniformly at random in each round. Here we are focusing our assumption that at each round we have a fixed number.
So this is kind of like sandpile.
It's a little bit like the sandpile model where you have once a certain threshold models, there are things.
But the generalized sandpile where you don't have to give it to one neighbor each, but some random fraction of the neighbors get
Correct.
a random two. There is some similarity to that.
Correct. Pure random process. So there are no algorithms in this talk. It's entirely about analysis of a process. Yeah.
Exactly a branching random walk, except that with coils.
Exactly. So it's a branching random walk combination with coalescing. That's why it's called a coalescing-branching random walk. Yes. Can you repeat that? Correct. Correct. Unless it got infected by somebody else, by one of its neighbors. Okay. So it's a very simplified model, and this you can imagine lots of variations of this model with potentially different amount of branchings chosen at random from a distribution, different amount of recovery, but then the more you do it, the closer and closer it might become similar to an SIS model, for example, that we talked about earlier. Okay, any questions about the Cobra Walk? Yes? You could put self-adjust and it won't change the definition. So you can have self-adjust, and perhaps that will make it more interesting for certain graphs like bipartite graphs where things are just going to go back and forth. But yeah, you can add self-adjust. Okay, so we keep on going. So what do we want to know about Cobra Walks? So in this talk, we are going to focus on one measure only. And you can again imagine lots of different measures. One measure that we focus on, this is a little bit motivated from an information dissemination point of view, like Marcos's talk. What is the cover time? How long does it take for a Cobra Walk to visit every node in a graph? Okay, that's the question. Now, for standard random walks, so if you so notice that this Cobra Walk where we had just k equals 2, if you put k equals 1, that's exactly the standard random walk. And standard random walks is very well studied. The result of Feige and also Brightwell and Winkler give you exact bounds, worst case bounds on this, which is 4/27 n cubed. So that's very well studied. So what we want to know is what does the Cobra Walk do? Other things that would be of interest, which we are not going to look in this talk, or what are the long-term dynamics? What percentage of nodes of a graph are infected as t goes to infinity, as if it makes sense? Is there an analog to a stationary distribution or mixing time? And one of the things was we were motivated by this by looking at different kinds of diffusion processes. So I'm going to talk a little bit about connections to different applications. But for the purposes of the technical point of the talk, the cover time is what I will be looking at. Okay, before I talk about that, let me just say a little bit about what challenges we faced in trying to analyze. Unlike, for example, in gossip models and rumor spreading models where, in Marcos's talk, where the number of active nodes is continually increasing, here the size of the active set, the size of the infected set is non-monotonic. So we can't really say, argue a cover time in terms of analyzing that size of the active set. The other approach often to attack such things is to view these tokens that I talked about as pebbles that are moving around in the graph. But there is a lack, because of coalescing nature, there is a lack of independence in the number of distribution of these pebbles. Now, the dynamics of the Cobra Walks is governed by the graph topology, and we will be looking at that more closely, and unfortunately also by the current distribution of pebbles. We really cannot say that in every round the number of pebbles is going to double if the number of pebbles or the number of nodes active is so and so, then the next round is going to double or it's going to increase by a certain factor. We cannot say, because it really crucially depends upon the distribution of the pebbles. Okay, so there are lots of motivations. I will just quickly go over this. You can view a Cobra Walks as a discrete time version of the SIS epidemic mode. But one important difference, and which also implies we are looking at slightly different measures, is that there is a probability 0 of extinction, okay, because of the way we have defined it. We could, again, change that, but that's the way we have defined it. But otherwise, they are very similar in nature. Branching simulates probability of infecting neighbors. Coalescing simulates receiving infection from multiple neighbors. In our case, the recovery time is exactly one step. But you can mind. And as Ganesh mentioned, there is a huge amount of work on related contact processes. And a lot of work focuses on extinction time and persistence. There is a lot of work using mean field approximations. We will be looking at only on the focus on cover time in this discrete setting. There is relations to rumor spreading as in how information disseminates. There is a lot of work, there is a very nice simple result that shows that a certain kind of rumor spreading methods finishes on any graph in order n log n time. The one crucial difference is the set of nodes with rumor monotonically is increasing. And we are trying to look at this as a potential way to spread rumors using lower message complexity, and there are certain examples where this is true. Finally, there is a long connection with parallel random walks. So if these things did not coalesce, then this would have exactly been parallel random walks. And one question is, can we draw from the work in this parallel random walks?
What is message complexity?
So one message complexity, so let's suppose you want to spread rumors. So let's say you adopted the following model where every active node constantly spreads the rumor. Okay? So then you try to measure how many messages are you sending overall before every node receives it. One alternative would be to implement it something like the Cobra Walk, where you define active nodes differently. The active nodes are the nodes that receive the rumor in the last step. Only they spread the rumor. This, in some graphs, could reduce the number of messages being sent.
So the message complexity is the overall communication.
Overall communication. Okay, so I'll start by telling you what we have been able to show, and then I will tell you what others also have looked at the problem and have been able to show, and then I will tell you the open problems, and then I will go over a couple of results in the space. Okay, so the first, there is a not fairly straightforward lower bound that I'll illustrate to you in a moment, that with high probability it will take you n log n rounds, n log n steps for, in the worst case, on the worst case graph for a Cobra Walk to complete. It is not difficult, but it's not trivial to show that on trees you can achieve that bound, and in fact for trees this is the tight bound. You can get an n log n bound for trees with high probability for the Cobra Walk to cover everybody. On d-dimensional grids, you can get a bound of n to the 1 over d. And we can go over the line case, which is a fairly simple argument, but I can illustrate that to you. The thing that, there are two areas that we have spent the most. Lower bound is not applicable for every graph. This is a worst case lower bound. There exist graphs for which, so you cannot, if you want to prove a general bound, you cannot prove better than n log n. But for many graphs, you can do better than, it'll cover faster than n log n, and we'll look at examples. So often you would like to understand how the cover time behaves as a function of the structure of the graph. And a natural thing to consider is something I'm referring to as conductance, which is very closely related to expansion, very closely related to the isoperimetric number. What we have shown is so if you look at constant degree graphs, constant conductance, we have shown an order log square and bound. But basically, in general, we have shown a bound for constant degree graphs, a bound that varies as quadratic in log n over phi. It's straightforward to show that log n over phi is a lower bound, but we have shown an upper bound of square of log n over phi. Very recent work, Cooper, Radzik, and Rivera actually have shown for expanders an order log n bound, which would be tight. The final result, and this is what and there is a big gap, is, meaning for a long time we have even struggled to show that Cobra walks are faster than random walks, regular random walks. And it seems very surprising. It seems like obviously they're much faster. And finally, we have been able to beat it, but just by a little bit. So from n to the 3, we have been able to show that it's down to n to the 11 over 4 times log n. It's clearly not the right bound. So I'm almost ashamed for putting this on the board, on the slides. But even this argument is somewhat technical, and I'll go over a high-level overview of this. Okay, so that's what we know. So there are a huge amount of open problems in my, if you feel that this is a class of processes of interest. So there's a substantial gap between upper and lower bounds for general graphs especially. Tight bounds in terms of conductance and expansion of the graphs are unknown. Other measures of interest, such as what are the, how long does it take to cover at least a large fraction of the graph would be of interest. Better bounds for special graph classes, we haven't looked at things like preferential attachment graphs and so on. And connect this to other processes that we have discussed in this meeting, as well as other processes that other people have looked at. All right, so I'm going to talk about these two results. I'll spend maybe a few minutes on each of those. Actually, before I do that, let me just do a couple of quick examples so that you can see what kind of things are going on in analyzing this. Okay, so one easy example, which will both illustrate to you a lower bound and is, let's take a star. Okay, so if you take a star, and if there is the node, if you imagine the infection is starting from here, then in each round, the infected node is selecting 2 random neighbors to infect. And then those 2 nodes, in this example, since we don't have self walks here, in the next round, those infections will go back to the same node at the root, and then it'll keep on going. So this is essentially a coupon collector problem that's going on. And if you just a standard analysis of coupon collector processes shows you that this will take you theta n log n. By the way, n is the number of vertices in the graph. Okay, see? For trees, it actually turns out to be more complicated because for general trees, you can have a fairly complex structure and you really do not know where in the tree the infection is residing. So you have to analyze, so the analysis requires you to consider the sizes of the different trees and how the infection travels and take care of various things. But ultimately, you can't show that for every tree also you get a theta and log n log. Okay, the other instructive example, which is also not that fairly straightforward, is looking at the line. Okay, so it's a one-dimensional grid and vertices. In here, what is happening is, let's say the infection starts at some point, and let's imagine it starts at one end. Then in the next round, this node gets covered. Now, in every round, you can see that this node is selecting 2 neighbors at random for both of the branchings. Then the probability that this node is not infected is less than half, right? So there is the bias towards the right, and that bias automatically implies that this will complete in linear time with high probability. So for a line, you actually get a linear bound. For a 2D grid, you get an n to the half bound, and so on. Okay, so those are easy examples. Let's look at what's going on with an arbitrary graph. So we're going to look at 2 results for arbitrary graphs, one in terms of conductance. Yes?
What happens in a tree graph?
It'll complete in log n rounds, yes. Okay, so the conductance of a graph, forget all this mumbo jumbo written in here, but basically the conductance of a graph is you have a set of vertices, you look at how many edges are coming out of the set as a function, as a ratio of the number of edges incident on the set. Okay? Number of edges coming out of the set as a ratio of the number of edges incident on the set. So that's the conductance of the set. Okay? Ratio of the number of edges between S and B minus S to the volume of S. Volume of S is just the sum of the degrees of the vertices in S. And the conductance of the graph is the minimum over all sets that have at most half the volume. Okay? And a constant degree, constant conductance graph is referred to as an expander. It has constant. Okay, so that's conductance. Now, as I mentioned, the challenges are the number of active nodes does not monotonically change. And though the pebbles make independent branching moves, coalescing introduces dependencies. So how do we analyze this? So the challenge has been, since we want to do some analysis where we really don't want to keep track exactly of which nodes are infected at each point of time, that seems too complicated. And so what we do is try to, in most of these analyses, we try to identify other processes that stochastically dominate this process in terms of the measure we are looking at and analyze that, okay? And prove upper bounds on that. So what we do is we introduce a new process, and here I'm just calling it W-alt, that stochastically dominate Cobra Walks. And we break the process into order log n epochs of length log n over phi square. And we show that in each epoch, any given node has a constant probability of getting hit. And if you're running it for log n rounds, then with high probability it'll get hit. That'll also give you an expected bound. Now, unfortunately, the way we have defined it, it seems really impossible to beat it unless we use some other clever way of giving up this extra factor of log n, which we would rather avoid, but we have not been able to. So that's one place where we would like to improve the analysis. Okay, so here is the idea. So let's imagine there are pebbles distributed on the graph. Okay, and here I'm starting with some number from delta times n pebbles distributed arbitrarily around the graph. And let's imagine in this process that really no more branching or coalescing occurs. You start off with this, and that's what these pebbles just do random walks. But they do slightly different kinds of random walks. We label the pebbles in an arbitrary order. Now, notice what is happening is the following. That since at each node, let's say this node is infected, it makes two random choices, okay? And it makes this choice and this choice. So it has sort of two units of randomness, in some sense. It has two pieces of randomness. So the way we view this is we are viewing all these pebbles moving around, but if more than two pebbles enter a node, then we want the third pebble not to make a random choice. So we say, well, the third pebble picks one of the first two pebbles' random choices. So the first two pebbles at V at any time t continue to move independently and random, but the third and higher ranked pebbles at V choose one of the destinations of the first two pebbles independently at random probability. So I claim that this process is stochastic, well, the cover time of this process stochastically dominates the cover time of a Cobra walk because the movement of there is no branching going on at all, and the movement of the pebbles is guaranteed to satisfy the coalescing aspects that we are enforcing. Okay. Okay. So here is an example. So let's suppose there were these three pebbles here. And let's suppose all these three pebbles came here. Then we let the first pebble make a random choice, second pebble make a random choice. Now the third pebble chooses one of the first two pebbles and does the random choice. Okay. So as I said, we saw that each node will be covered by at least one pebble in order log n over phi square steps with constant probability. And we repeat log n times. So we need to show that any pebble I is at vertex V at time this with is theta 1 over n. Okay, so what we're going to show is that there are delta n pebbles, and we're going to show that any pebble I is at vertex V at any particular given time is theta 1 over n, and this will give us the bound of at least a constant probability of visiting that vertex. And we can't use standard methods because walks are not fully independent because of this. So I'll go over this relatively fast. So we associate an event EI with the event that the pebble I visits a node V at time S. Then the probability that V gets visited by any of the pebbles is the union of these events. The union of these events is the sum of the probabilities of the individual events minus the intersection of the events. Standard random walk theory can identify for each of these individual pebbles, but the challenge is to bound this. And now this is the version where you're looking at two distinct pebbles, right? So what we do is we look at the walk of pebbles, and then we capture the walk of the pebbles in a product graph, which is a tensor product graph, and we look at the directed version of this graph, and using directed Cheeger's inequality, we are able to connect the time the stationary distribution and the time taken to converge to the stationary distribution in terms of the smallest eigenvalue of the normalized Laplacian, which in itself is related to the conductance. Okay, so that's the basic process. So we model it using this alternate walk, and look at the alternate walk and study it in a product graph, and that's how we connect the two together. Of the tensor product graph. Yeah.
Why did you assume that there is an fraction of the group that has become?
Good. Now this works. This works regardless of the location of the pebbles. So you can in fact imagine that all the pebbles are located at any subset at one node of the graph. Okay, so this works regardless of where the pebbles are located. Okay, so in the final 3 minutes, I will try to convince, maybe not convince you, but at least show you a very glimpse of how we were able to beat the n-cube bound. Can we beat the trivial n-cube bound? We tried various ideas. I mean, there's a beautiful paper by Brightwell and Winkler which shows the 4n-cube over 27 result for the standard random walks. But to show our bound, we actually used some ideas developed a new notion of a random walk, which is related to a well-studied class of walks which are called biased random walks. And I will say a little bit about it. Essentially, we are trying to understand the hitting time, okay? Using standard relations between hitting time and cover time, you can argue that cover time is within log n factor of the hitting time, so our focus is on hitting time. Okay, so the question is, just focusing our attention on the following question. Here, the Cobra Walk starts at the source. How long will it take to hit a particular target T? So, there is a very nice result due to Azar, Broder, Carlin, Lineal, and Phillips from '92, which looks at these kinds of walks where it's like a standard random walk. In each step, with 1 minus epsilon probability, it does exactly what you would do for a standard random walk. But with epsilon probability, some controller who wants to achieve something decides to make the move. Okay? And they give, analyze it, and they say, okay, there exist certain walks that can give certain kind of stationary distributions. Okay? Don't worry about the exact statement of this, but basically they try to understand these walks and try to understand what do stationary distributions look like. So imagine a deregular graph, then the stationary distribution means everybody has the same probability. Question is, if I give you this additional epsilon probability of controlling it, can you increase the stationary probability, is the question. And they answer, yes, you can increase it, and this is how much you can increase by, and so on. Okay, that's the meaning of state. Now, we define, so notice that in our case, look at our situation where, let's say we have a graph, we have a vertex S where the infection starts, and we want to reach this target T. And we want to find out how long this infection takes to reach the target T. So the way we analyze it, and it seems rather weak, but we try to understand, well, in the next round, 2 nodes might get infected. Let's see, the first node is doing a standard random walk, and the second node is also doing a standard random. The first token is doing a standard random walk, second token is also doing a standard random walk. But we don't have to follow both of these. We could try to follow one of them, let's say the one that is closer to T, for example. Okay? So we define something called an inverse degree biased walk, where with probability inversely proportional to its degree, the controller selects the neighbor. With probability 1 minus 1 over the degree, it moves to a uniformly random neighbor. And we are able to show that if you analyze this walk, the hitting time to x is stochastically dominated by the hitting time of this inverse degree biased walk. So that's the walk we can try to analyze. So we we look at the shortest path from the source to this, and then we look at the walk as it's going from here to there, the Cobra walk as it's going from here to there. And just like in the standard, in many random walk situations, we are trying to understand how long does it take for this node to get infected, then for this node to get infected, then for this node to get infected, and so on. In order to analyze that, we have to understand the return time to each of these. So in order to understand the return time to that, we have to understand the stationary distribution. And in order to understand the stationary distribution, we make use of this really beautiful result due to Metropolis et al. From 1953, which shows that given any distribution, given any strictly positive probability distribution pi, it specifies what Markov chain M, what Markov chain M over the graph will give you that stationary distribution. Okay? And we are able to use that in conjunction with the ideas from Azhar et al. To develop the order n to the 11 over 4. But the main point I want to emphasize is that it entirely tries to follow infection going along a certain path. And it seems really weak because Cobra walks are going all over the place, so you can have infections reach T from various places, but we really focus our attention on one path and are able to argue that things can go faster than it will go, for example, in a typical random walk. Okay, so I think so these are the various open problems. We have some tight results for grids and trees and somewhat tight for conductance space analysis, but many open problems remain. I've talked about these before, and I think I'll stop at this point. Thank you. Yeah.
So is one way of understanding your analysis technique is that basically say I have a random or maybe a bunch of random walks on the shortest path tree, but these random walks, the values can disappear as well.
Yes, yes. So I won't call it necessarily a shortest path. Yeah, you could view it like that. Yeah. So the walk is going along the shortest path. So in this, for example, the walk is going along the shortest path, but it is leaving, and it is leaving the shortest path tree itself, for example. The main thing is we want to be able to say that the return time to this is faster than in a regular random walk. So to look at the return time to this itself, we have to use the Cobra Walks properties. And that's where we have this inverse degree biased walk. And it depends on some structure of this, and so that's why this n to the 11 over 4 comes in, because it depends upon the degree, the sum of the degrees along certain paths. So we give the worst case bound for the sum of the degrees along the paths, and that's what leads to this.
What I understand is the case that, so you said that you lose a log n from going from hitting time to log n.
Yeah.
So overall your bound is like n to the 11 over 4 times log.
Correct.
So I'm wondering whether that can be split as n log n for whatever is happening on the tree, and then your return times are whatever remains. So
yeah. Oh, good, good. That could be true. Yeah. So the one of the ends could be directly coming from this path. Yes, that could be. That's most likely true. Yes. Yeah. Yes, Marcus. No. So the question was, is there a good notion of a mixing time for this walk? But no, we didn't. Yeah.
Do you have a sense for the worst case graph?
So I think the star is a worst case graph. I think maybe that the conjecture is it's actually n log n. So in which case star will be the worst case graph. The standard lollipop graph takes n log n. So we don't have any bound worse than n log n.
You say for k greater than equal to?
For k equals 2.
Okay.
So and so for k greater than 2, of course it is. So we have not tried to bound in terms of k. You might get something in terms of k, but we have not bothered doing that at all.
And a lollipop takes n log n. Once you get up the path, it's not that you disappear. I mean, you still take n log n.
Correct. I mean, you could disappear because of the traction of the clique here, but still, you eventually do make it. Yeah. Okay. Thank you.